Hello, can you hear me?
Oh my god, okay. He's on the screen.
Can you see my slides?
Yes.
Excellent. Okay. Hello, everyone. Thanks for accommodating me with this virtual talk. And I'm going to talk about secure ML inference running as fast as plain text. So you can see my slides. You can hear me properly. I can just go.
Yes, Rahul, you can go.
Excellent. All right. So this talk is about the problem of secure inference, right? So here we have an entity Bob, which has some sensitive data like medical images, say CT scans, chest X-rays, and then we have a hospital which can have an ML model for inference, and they want to do inference together. But hospital does not want its ML model to leave its trust boundary. Bob does not want its sensitive data to leave its trust boundary, and still wants to get the inference result, right? So in secure inference, this inference happens, but hospital should learn nothing about client's data, and Bob should learn only the model output, right, and nothing else about the hospital's model. And this we know can be solved by the tool of secure multiparty computation. So this is the problem of secure inference, which we are going to talk about. And why is this problem important? So if we look at what is happening currently in industry, then there are releases like these. And here I have taken a screenshot from OpenAI's website when they released ChatGPT Enterprise. So they say some good things, right? They say that their data is encrypted at rest with AES 256, and the data is encrypted in transit as well. They are compliant with some standards. But what stands out is this line, right? Which means that customer prompts and company data will not be used for training OpenAI models. But they have that data, right? Can they do something else with it? And this is like a pinky promise, right? It's not technically enforced. So what we will like to do is technically enforce this promise, right? Our high level goal is that all machine learning inference services should be using secure inference. Because if they use secure inference, if they use secure multi-party computation, then the following claims which enterprises are today making can be technically enforced. Like that sensitive data are not used in training by model owner. Well, model owner only got a secret share, so they cannot use it for training anything. Model owner deletes inputs after 30 days. Well, they only had a secret share. There's nothing to delete. Sensitive inputs cannot be passed by model owners to untrusted plugins, right? They don't have the data, so how can they pass it to a plugin? And models fine-tuned on private data cannot be queried by model owners, right? So what happens here is that you have some private data, you fine-tune a model, and then you can query that fine-tuned model, but can the model owner also query that fine-tuned model? But if you can say secure fine-tuning, then the model will be secret shared between the data owner and the model owner. So unless they get together, the inference process cannot happen. And many more of these things can be technically enforced. So secure inference in general, hopefully I've convinced you, is a good idea and should be done. But while I'm talking about all this cool, secure, Kool-Aid things, there are monsters to smack me down, right? First monster is efficiency. Well, secure multi-party computation comes with its own overheads, which we are all familiar with. And then even if we have some technology which is secure, which is efficient, there is a bigger monster of standardization, right? Unless there is a standard which companies can point to saying that, look, we are compliant with that standard, people are not going to buy into the technology, right? And in this talk, I'm going to focus my talk on this smaller monster of efficiency, and we'll talk a little bit about standardization at the end. So, what is the landscape of secure inference? How does it look like? So, this area really got traction some 6 years ago with the work of Secure ML, right? And at that time, we were able to do like small MNIST scale models, right? Monochromatic images. And then models scaled up, the technology scaled up, and we were as a community able to do CFAR scale models. So, colored images, but small images. And then this work got scaled up in which things started becoming really interesting. We were able to do models with millions of parameters. And if we have millions of parameters, then we can do cool things like prognosis of lung diseases from chest x-rays in a completely private manner. And recently, uh, we have pushed the boundaries to even billions of parameters. So once we can do models with billions of parameters, we can do GPT class models, right? And I'm going to talk and show you results about these works, Orca and Sigma, in the next few slides. So here is, you can say, our main result, like which is answering the question which was raised in the title of my talk, right? So if I take a model like VGG16, it is a model with something like 138 million parameters, and we run it on the task of ImageNet inference, where ImageNet is a 1,000 class data set, which is widely used in machine learning. And I take this and run it on Google Colab, right? Then depending on what hardware Google gods bestow upon me, the running time is something between 0.2 to 0.5 seconds. Now, if we run this same task in a trusted execution environment, right, then there are some security overheads. And if I do this very naively, then with Intel's SGX, this task can take over 2 seconds, and same with NVIDIA's Ampere protected memory. And 3 years back, when we ran this task with 2PC, then our slowdowns were something like 6,000 times, and this task would take 40 minutes. And then we threw the hammer of FSS on it. And I'm going to tell you what FSS is. It's function secret sharing, in which we break down our computation into a pre-processing phase and an online phase. And by focusing on online phase, and making it more efficient, we can get an online time of 44 seconds. And finally, we threw GPUs at this problem, which led to this result, which was even we were not expecting. We got to the time of 0.53 seconds, right? So this is like only 1 plus epsilon overheads over plain text. So all in all, secure inference is now at a stage where the secure inference latency matches what users are expecting from plain text. So now I will go down into some background of the terms which I have mentioned in this slide. Right. So first question is like, what is our threat model? So we are in semi-honest 2PC with pre-processing models. Here, a trusted dealer generates some correlated randomness and gives it to the parties who are going to do this secure 2PC, right? And this happens before parties have even brought in their secret inputs. And then there is an online phase in which parties bring in their secret inputs and consume this correlated randomness which was generated in the pre-processing phase to compute the output. And this is the same model which is used by other people as well, Metascriptin or Infer, or recent work of Piranha by UC Berkeley. Next, what is function secret sharing? So this is a really cool object. In function secret sharing, you have a function f, and you can secret share it into two functions, f0 and f1, right? Which have this nice property that for any input, if first party will locally evaluate f0x and second party will locally evaluate f1x, then they end up with secret shares of f of x. And these functions f0 and f1 are called FSS keys. So we have this correctness property that just by local evaluation, you can end up with secret shares of the output, right? So this brings down the the communication requirements of MPC by a lot, right? Because most of the work is happening just non-interactively. And the security guarantee is that F0 and F1 individually don't reveal anything about F. So overall, with FSS, communication goes down dramatically, but there are storage overheads of storing these FSS keys, and computation using FSS keys is more expensive, right? So communication goes down, but storage and compute go up, and these are the performance bottlenecks that we are going to address. So if we take these FSS-based protocols and run them on GPUs, then GPUs take care of the compute, right? And our performance bottleneck becomes moving these FSS keys from RAM to the GPUs for computation. And so reducing this key size becomes really, really crucial. At a high level, what we have done, we have shifted bottlenecks of secure inference from communication-heavy protocols two protocols which are spending a lot of time in compute. We threw GPUs at the problem. Now compute is not an issue, but the issue is transferring these keys between RAM and GPU. So to do that, we create new cryptographic protocols for operations occurring in machine learning. So if we look at VGG16 network, then it has some convolutions followed by truncations, max pools, ReLUs, and convolutions are themselves not very expensive. We have efficient protocols for them, but the other three are. So we saw the previous works. They had some key size, right, which I have shown analytically here. And then we constructed new cryptographic protocols which have much smaller key size, right, 2x to 5.7x lower. And with this, I am ready to talk about our evaluation results. So we have a setup in which there are two machines which are connected in a LAN setting, and each machine has a GPU and a CPU and a RAM. And when we ran on ImageNet, then here are our results. We took famous ML models, right? And you should look at the rightmost column, which is Orca, which is our time. And you can see we are running this ImageNet scale inference in sub-second, right? And our baselines are Llama, which is function sequence sharing running on CPUs, right? And we can see that we are like more than 100x faster than Llama on VGG16. And another baseline is Crypt', which is not FSS, but still 2PC with preprocessing, and it uses GPUs, right? And even with respect to Crypt', we are 8x to 24x faster. Now, I started this talk with talking about OpenAI and GPT, right? So how do we fare there? So we extended our work to transformers, and here I am again evaluating with Crypt' as the baseline. So Crypt' is at 1x and sigma is our work. And we can see that our protocols, when run even on CPUs, are able to match Crypt' on GPUs. And when we accelerate our FSS-based protocols for GPT inference or transformer inference with GPUs, then the speedups are very high, right? More than 10x across the board, sometimes even closer to 20x. But these models like BERT or GPT-2 or GPT-Neo, uh, so BERT and GPT-2 are still in hundreds of millions of parameters, and GPT-Neo is 1.3 billion parameters. And there is all this buzz about like 7 billion model by Meta and 13 billion models. So what happens there, right? So when we talk about scaling to practical GPT models, then we see that Crypt' runs out of memory at 2.7 billion parameter models. So we cannot run our 7 billion or 13 billion parameter models on it. And our system, Sigma, scales well, right? But Sigma running on CPUs, the time increases very sharply. But Sigma running on GPUs, we can run even a 13 billion parameter model in 30 seconds. Okay, so this was all about the tech and the evaluation. Now, the third thing is usability, right? We have done all this work. Can someone use our work? So for that, we have created a push button endpoint creator, right? So you run PyTorch, you train your favorite ML model, you export to Onyx and pass it to our toolchain. Our toolchain, what it will do is it will create this nice looking website which can be exposed to a user. And here on this website, the user will be told something about like the FSS model. And here this model is simple, right? This is just handwritten digit recognition. The user can select an image, right? Upload it, and then get masks from dealer, and then mask this user sensitive image using the mask, and then you get like this gibberish looking image. Now secure inference can happen on this gibberish looking image, and here we will see that the prediction will come out correctly as 7, right? So we took ML model, we created an endpoint which normal users can use, right? Now, what will the users use it for? So one of the high-level abstract application is secure model testing or try before you buy. So what happens here is that there is a testset owner which has some sensitive data and wants to deploy AI in their hospital, and they want to know which ML model works the best, right? And there are many ML vendors, each claiming that their model is the best. Now, this test set owner cannot really make this data set public, right? Because then ML vendors will just overfit on the data and claim they have 100% accuracy. They, the ML vendors have also trained these models on their own private data, right? So they cannot also just take these models and give them to the hospital. So what we can solve this problem just by repeated instances of secure inference, right? And now I'm going to show you a concrete evaluation for this abstract scenario. So Stanford has a Chexpert model for prognosis of lung diseases from chest X-rays, and Carpal is a lab in India which has Indian patient data. And Carpal wanted to know that how well does Stanford's model perform on its data, right? And we were able to do this using secure validation based on secure inference. And the only thing which was revealed to both parties is that the AUROC score of the model on Indian patient data was 0.9, right? Nothing else was revealed to anyone else. And this was a 7 million parameter model, so we could do it easily, right? And could do prognosis of 14 lung diseases. So where next, right? We want secure inference to be deployed in everyday life like TLS, right? All ML inference as a service are using TLS for encryption during transit, but we want them to use encryption during compute as well. Right? So this revealing your private data to model owners by default, we want this to be disabled. And to do that, as a community, we'll have to move towards education, telling people that look, secure inference is something which exists and we should be using it, to creating standards which we can then tell the enterprises to be compliant with. And hopefully the regulators will also catch up and ask enterprises to be compliant with the standards. Some research directions. I've talked about inference, but training is equally important. So here you have two parties or three parties or four parties, each with their data sets, and they want to compute a joint model together, right? Without revealing their data sets to each other. This is one problem, which is about increasing the number of parties. But even if we take the two-party case where FSS is applicable, still we are far from doing ImageNet scale training, right? And working on this problem, I have observed that GPUs might not be the best fit because the data comes in a very streaming fashion. So FPGAs might be better, right? And we can look at using FPGAs to accelerate secure inference. And at the end, I have given some links. The first is the link to our project. The second is GitHub. All our work is open source. Nothing is patented, so you can use it for whatever purpose you want. And you can contact us, the whole team, at easypeasy@microsoft.com. With that, I'll end my talk. Thank you.